2026 job market is brutal. Interviewers are not just asking for us to draw boxes that you see on the screen, but they're also asking for low-level implementation details. When you say rate limiting, they just don't expect you to draw a box of API gateway, write rate limiting there, but they also expect you to tell what algorithm are you going to use, why are you going to use it, and what are the trade-offs that comes along with it. If this is the information that you're looking for, if this is the kind of prep that you want for yourself, please stay tuned, and we are going to cover 5 different rate limiting algorithms in this video. So let's go one by one. The first one is a very simple one, fixed window counter. Here, what happens is that you always take a window of say 1 minute, and in that window, you're allowing 100 requests. And this is always already divided. So it's already like you can see that there are windows drawn. So this is 1 minute, this is 1 minute, and so on. And from this to this, 100 requests are allowed. Now, many of you would have already understood the problem with this algorithm. The problem with this algorithm is that if you're counting within this, and then the moment you cross over this region and you're again resetting the count, there will be a period in which you may allow more than 100. In fact, you can allow 200 requests in less than 1 minute if you follow this implementation. It happens something like this. If you see, in this window, we got 100 requests. And in the next window, again, within 1 minute, suppose this orange or red box is also 1 minute. This is 1 minute and this is 1 minute. So in this orange 1 minute, this window brought in 100 requests. And then this window got in 100 requests. So a overall total of 200 requests was allowed within just 1 minute. So that is the problem with the algorithm. But at the same time, it's really simple. And at a given point in time per user, you're not risking more than double of what you intended to allow. So it's not as dangerous again. So the implementation is really simple. You will always know what is the window start for a user and what is the count that you have allowed till now for the user. And this counting, almost all rate implementation counting is done on a user level. Okay. Or it can be IP addressed or request ID or any of the other identifier that you are using to identify the user or the machine. But it is generally on a user level. There are other sort of rate limitations that are put as a whole on the system, but that's not what we are covering right now. What we are covering right now is per user, how you can save your system from exploitation. Okay. So getting back to the code, here it's very simple. A request came in and you just get the counter for that user. And now if the window start, which was already recorded in this counter, plus 60 is greater than equal to now in the current time. So it's a new window. A new window has started. So you will just reset the count to 0 and you will set window start to now. And now after that, if your counter.count is less than 100, that means you have not yet served 100 requests. Then you'll simply return true, allow it, and increase the count. So you know how much you're serving for user in that window. And if the window expires, you're going to reset it and set it as 0, the count. So it's really, really simple. Some of the things like how now is derived, just don't, this is pseudocode. Don't want it to bloat the code for the sake of it. So just this is the overall idea of how the code would look like. For implementations, more code needs to be there, right? So as we discussed what the problem is with this algorithm is, we'll see how we can fix it with other implementations or other algorithms, right? Before that, let's just quickly see what's the time complexity and space complexity for such type of system. So for this fixed window counter, the time complexity is order of 1 because you're not really storing anything but some constant variables. And the space complexity is order of users because for each user, you're storing that counter, right? Okay. Now, the other thing is sliding log algorithm. So here, the implementation is slightly different. In this, we overcome that problem of serving 200 requests in just 60 seconds, which was sort of against of what we wanted to do from the start, right? Requirement was in 1 minute you can serve 1 minute you can serve 100 requests. The previous implementation was not able to sustain or satisfy that condition. So in this algorithm, we will see how we can do that. So in this algorithm, The core idea is instead of just storing the counter, you store all the requests that you get. Okay. So let's understand this with this timeline. In this timeline, we see that this is 0 second, this is 60 seconds. So this is a window in which till 5 seconds, you got 30 requests. So you'll allow it. It's under 100. Till 60 seconds, you got 100 requests. Okay. Now, we'll also see that at the 5th second to 60th second, you've served a total of 70 requests in this just small window alone. And after that, in just 5 more seconds, 10 more requests came. In previous implementation, this 10 request would have done nothing to the previous. Like it would have done or it would have no relation to the previous window. But in this implementation, the last 60 seconds matter and the last request served within those 60 seconds matter. Okay. So here we are going to check that from the 65, we'll go back 60 seconds in time and we will see how much have we served. So we have served 70. You're asking for 10 more and it is still less than 100. So I'm going to allow it. Okay. You'll see this here also that from 1 to 60, I am serving 100 requests. From 65th, I'm also asking for 10 more. But it is still less than 100 if you just take the last 60 seconds. So I'm going to allow it. However, if this request was say 40, so 40 plus 70 would have been 110 and those last 10 requests would have been rejected because in the last 60 seconds, we have already served 100 requests, right? So again, very simple concept. The implementation is also simple. For each user, you will have a DQ of the last request times. Okay. So whenever a request comes, just pull that queue from the array of or the map of user comma DQ, and then you will get your queue, and then you will do one simple thing that you will first clean the queue. Anything that exists in queue and is older than last 60 seconds, just delete it because it's of no use anymore, right? The only last 60 seconds from now matters. So this now minus 60 from the start of the queue, if anything exists, you do a peek first, you get the element. If it's less than now minus 60, then it's old. Just get it out. So just poll it. Now, if your queue still is less than 100, that means that you have not yet served 100 requests in the 60 seconds. So that means you can serve this request. So we'll add this request in the later part, in the right side of the queue. That is why we're using a queue so that we can delete from this side and insert this side. And then you will simply return true. However, if the queue size was not less than 100, then you'll return false, right? Make sense? Here, the time complexity and space complexity. As you would guess, space complexity is order of total request, or the better way to put would be total request per user into user. Fair? And the time complexity is expired requests, or if you amortize it, it's order of 1. It is again constant because you do poll things here and you add things here, but it's all constant operation because this is sort of, it's never gonna breach a lot in n terms, right? So it will be amortized order of 1. Okay. Now the next algorithm is sliding window counter. Now this is where we start looking into some of the actual productionalized algorithms, the algorithms that are actually used in modern systems. The other two that you saw, you could understand the problem, right? The first one was not even sufficing the requirement, and the second one was using extra space, right? So now we are getting into the world of actual production algorithms, and here concept is still simple if you just try to understand in mathematical terms. Let's look at it. So for sliding window counter, you take two things. Okay, I'll just take a laser pointer and see. So this is your previous window start, that is 0 seconds, and this is your 60-second mark, and this is your 65th second mark. Now just imagine that till 60 seconds, your system was able to serve 90 requests. Okay, and then in the next 5 seconds, you got 15 more requests. Okay. Now, what you will do is you will try to find out that if I minus this 5 seconds from this side, how much request can I get out? How much request can I delete from my 90 number? That's the core idea. How do you do that without actually storing the actual arrival of request or storing request? By using a simple approximation that in 60 seconds, if I'm doing 90, so in 1 second, I'm doing 90 by 60. So in 5 seconds, I'm doing 90 by 60 into 5, right? Basic maths, 7th class or 6th class maths, right? Unitary method or something it was called. So you calculate that for whatever window has passed this 5 seconds, in the previous window, what was the rate? And by that rate, what are the requests that are already deleted or are not to be considered anymore? So in this system, 5 seconds have passed, 55 seconds are left. 90 into 55 by 60 is 82.5. Plus 15 is 87.5, 97.5. So what I'm doing here is I'm seeing that only 55 seconds of the 60 quota remains. So 82.5 is something that I still need to consider. Plus 15 is what the user is asking for. And this 82.5 plus 15 is still less than 100. So I'm going to allow it. However, if this 15 would have been 25, I would have rejected some 13 so request, whatever it is, right? Anything above the 100, we can't take. We can't accept. So core idea is whatever time has passed, try to negate the effect of it. Try to delete the effect of it. How do you delete the effect of it? By calculating approximately how much it would have been contributing. Now, some of the smart ones among you would have already found the issue with this algorithm. The issue with this algorithm is this is assuming that things are happening in a linear fashion, that requests were coming in uniformly at each point in time, so that this number 82.5 makes sense. However, in real world, it can so happen that all requests came only in this portion of the world. In that case, one request came here, so your window started. Then 90 requests or 89 requests came very later of the window. In that case, doing this 82.5 for this window will actually be wrong, right? So your system still will get abused a little less than the previous algorithms, but it's still not like concrete. Okay, that you're still sort of not guaranteeing 100 requests per minute. That is still getting breached. Okay. So let's look at the algorithm. The algorithm is again simple. First, you set the limit and window. These are final variables. This is just to set what is the requirement of the system. And then you take four things. Previous window start, previous count, current window start, and current count. Suppose an allow request comes, you will first calculate the current time, that is now. And then what you are going to do is you're trying to find the window that you are in. Okay. Now, this is a beautiful mathematical operation. When you do now by window into window, in our normal mathematics that we do on paper, we would just cut this window by window, right? However, computer doesn't work that way. Computer will first implement this bracket part and then it will multiply this into window. This will give you a hard number 1, 2, 3, 4 of whatever window it is. How this helps is here, explained here. Say now is 65 seconds. Okay. Now is 65 seconds. So, and window is 60, you know already. Now minus 60 is nearly 1 into window is going to give me 60. Because I am again getting a long. Okay. However, if it was 125 by 60, it would have been nearly 2 and into window would have been 120. So I always get the correct window start, whether it is 120, 125, 130, 170. Till I touch 180, it is going to give me 120 because of this bracket. So I always get the correct window start that I am in. Okay. Suppose I surpass it. I am in 185th. Then it will give me 180, which is the third window, right? Now, I am always storing the current window start already. And if this current window that I just calculated is not equal to current window start, then you guessed it right. This has to update the current window. So current window start value will go to the previous window start. The current count will go to previous count. Current window start will take this new value and current count will become 0. Okay. Now, this is just sort of a cleanup. This won't happen in every request. This will check, but if your current window is not changing, if one request is 125th second and the next is 127th second, then you will not even get into the sales block. Okay. What you will always get into is this part. Here, you will calculate what is the elapsed time now minus current window. This is always going to tell you that this was 120th second and this is 125th second. So 5 second is the elapsed time. You are going to calculate the weight of window that is always 60 minus elapsed, which is say 5 seconds. So 55 by window that is 60. 55 by 60 is something that I want to bring from my previous window. The same mathematics that we did there. 55 into 60 into the previous count into weight. So basically 90 into 55 by 60 is something that I'm borrowing from the previous window. Okay. Plus the current count of this window, which whatever came in this 5 seconds. So 55 from the previous window, 5 seconds from this window is going to give me the total 60-second story. Okay. Now I will check that whatever total is getting calculated, if I add 1 to it and if it's still less than limit, then I can allow it. I will update the current count and I will return true. However, if it's not less than limit, I will return false. Okay. So this algorithm really works in most cases. Just you know what's the issue. The issue is it works on the principle that requests are uniform, which may not be true always. Okay. Now the time complexity is again order of 1 because we are only using constant variables, and the space complexity is order of users because we are storing these 4 variables per user, all the users, right? Now we'll go to the fourth algorithm, which is token bucket. Now this can sound a little, uh, scary or really difficult to start with or understand, but it's really simple, right? What happens is, look at just focus on this diagram. What happens is you have 100 life. You are playing a video game and you have 100 life at start. Suppose you're fighting a master or a villain and he punches you. So you lost 50% of your life. So you come here. But the game rules are each and every second you survive, you get 1% life back. Okay, that's the rule. So the moment you survive 1 second, you punching and he is punching and the time is passing. So each and every second that you go forward, 1% life gets restored on its own, right? You don't have to type in Hesoyam or any cheat code. It happens automatically, right? So the moment 1 second happens, this life becomes 51%. Okay. Now, what is the max that it can reach? Say you are playing for 200 seconds and you were hitting him for 200 seconds and you didn't lost any life. What will happen? Will your life become 200%? No, right? Your life will become just what it can be at the max, that is 100%. This is exactly the same concept of token bucket. Okay. In code, what happens is a user starts with a token value of capacity, that is 100 in our case, and we have a refill rate with which he will get his life back, or the user will get the tokens back per second. What is the formula? Simple. Capacity by a minute or any window you want to choose. In our case, we are always taking 100 requests 1 minute. So in our case, capacity is 100 divided by 60 is our refill rate, which amounts to 1.67 request per second getting added to person's token balance. Okay. And suppose I give one request at 0th second and the next request I'm directly giving at 30th second. Do you want to run a loop for each and every second and update every person's token balance? No, right? The next time the person will come, be it 30th second, we will retrospectively check how much this person should have and give it then and there. We will not run a loop. Why do you want to run a loop when you can just do it when it's needed, right? So this is the same concept that we do here. Let's look at it. What happens is, person will get a request. We'll calculate now. We will calculate when was the last time we give this guy a refill. Okay. And we get this elapsed time. Elapsed time into refill rate is what the person should be adding to its token value. Okay. Which is this. So token, which was the previous balance, plus this should be the new value. But as I already said, it can't exceed the capacity. A person who is not hitting the system for 3 minutes will not get 3 minutes worth of token. At max, he will get 1 minute worth of token. So now the token value is going to be the min of capacity versus this value, token into token plus elapsed into refill rate. Okay. Now I will update the last refill time and I will simply run this logic. If a token is available, use it. Otherwise, return false. Okay. Now you can already assume the problem with this. The problem is that it allows burst. Now this is not really a problem if your system as a whole can take a lot of people using 100 requests right at that 1 second. So there are 5 users, okay, and all 5 users are immediately asking for this 100 immediately, like at 0th second, all of them at once. Then your system, which was designed for per user 100 requests per minute, has to actually entertain 100 requests per user in 1 second. So if your system is capable of that, you can use it. Otherwise, a tuned model of the same algorithm is also used where the initial balance is actually less. It is not 100 capacity. In this system, in this token bucket, like you can actually modify it basis your need, right? This system, some people love it because it allows the burst. Burst basically means that a user can use a lot of requests in bursts, like five, then a little gap, and then five immediately again. This is called burst. Like how gun shots are, how shotgun throws 4 bullets at one point and then there is a long gap. That is called burst. So this algorithm allows burst. That's the core feature. But it can be a blessing or it can be a problem. This is the requirement of your system. Okay. Now the last, which is again a little confusing to some people, but I'll try to make it easier, is leaky bucket. What happens in leaky bucket is it is exactly opposite of token bucket. Leaky bucket makes sure that no matter how the request comes in, whether it's in burst mode or it's uniform, the system will entertain the request in a linear fashion, in a smoothen fashion. This is called smoothing of the burst. Okay. So what happens, you can look in this diagram and you can understand that this is where the system right now is, the capacity of the system right now is in this red line. So if any request comes in, it is still less than, like there is still space, so it will be there. So say right now, if I have to modify this a bit, say this is the level right now, and I can add some request here, some here, and this will take till the brim, but it will only process one by one or whatever is the rate that you want to define. So how the requests are being used is a separate funnel altogether, and how requests are coming is a separate funnel altogether. So you can bring 10 requests and your bucket may still allow to keep it, but the request processing will happen in a linear fashion that your system will always guarantee, right? Your system will not get into load. I don't want to exactly compare it like apples to apples, but you can compare it to IRCTC Tatkal booking system, which is not caring about burst. It will care about what it can handle. So they would some way use a version or a principle of leaky bucket only to handle the rate that which they support user browsing. Right? We all know one wrong click and you're out of the whole window. That is a whole separate way of user validation and stuff. But yeah, so getting back on how this is implemented, you will have to keep the request actually in a queue because you are processing it later. So you can't actually take a decision on the fly. You have to store it. And which is again why space complexity is not the best here. It is worse than the previous method. But it is a really guaranteed system. It's a battle tested system for guaranteedness. Like it is guaranteed that your server will not suffer from unexpected burst. So for that, this is the trade-off, which is pace. Now let's get back to the code. What happens here is you have a queue of request which you are calling bucket, and you have a capacity 100. Okay, you have a leak rate of again 1.67 requests per second, and you have a last leak time which is currently initiated as now. Now a request comes in, you will first leak the expired request. Okay, I will get back to that method, but for now just imagine that this is happening, and then all you're doing is, if your bucket size is already at capacity, if this line is here, then you will not actually take any more requests. That's just waste of storage. Your storage should always be bounded. You can't take 100 million requests in your bucket. So there is a limit to this also, right? Which is capacity. And if it's already at size, you'll return false. You'll not even entertain this request. Otherwise, you'll add it and you'll return true. And you will return sort of this thing that, yeah, it will be taken care of. Now, let's look at how the requests are handled. What happens is, you calculate per in this call how many requests I have to actually take, which is elapsed. First, you calculate the elapsed time, and then you multiply it with the leak rate. Now you got the number of requests that you have to allow or leak, and you simply run a loop, and you basically poll the request number of leak times and process the request, and then you update the last leak time. Now again, this particular implementation is one way of writing leaky bucket. In a lot of systems, this is not the right way. The right way is to run a loop every second to pull out of this bucket, not every request. Because say your queue is having 100 requests, and 100 and like say 50 requests, and 51st request is coming sometime later, then you can't wait, because these requests are deserving to go to process, right? So you do this more often, basically, not per request. So this is just a simpler understanding and following the pattern of what I've done earlier, but there are variations to this, is all I want to say, right? Again, space complexity and time complexity wise, it's a little bad. Time complexity is order of request, and space complexity is order of users into order of request. Actually, this needs to be updated. Okay. So yeah, this was it about rate limiting. I am planning a lot more videos deep into system design concepts, where I'll not just draw boxes, I will actually go inside those boxes and see and explain what happens inside rate limiting, what happens inside a load balancer, what are the different load balancers available, what are the trade-offs. So for the such sort of videos, I really appreciate if you can hit that subscribe button and also press the bell icon to get notified for any such videos that I put out there.